My name is Beata Borysiuk, and I, in fact, come from the Wrocław University of Science and Technology, the Department of Biomedical Engineering. And today I would like to tell you a little bit about a quite interesting topic, which is the chemistry between space and AI. And it may seem a little bit mysterious, but let's take a look at our little agenda. So first of all, I'll talk about something that we call comms and how do we research them, so some research methodology. And then I'll switch to AI. So I'll tell you a little bit about AI-related concepts and how astrochemistry could benefit from applying AI methods. So without further ado, let's get started. And what are comms? So this abbreviation is the abbreviation used for the term complex organic molecules. And this term is in fact quite different for astronomers and chemists, because in astronomy, we tend to call the complex organic molecules the molecules which have multiple carbon atoms. So, for example, benzene or acetic acid, and many, many more. So they may seem not so large, but these molecules have been detected in interstellar space with radio telescopes. So this is an interesting thing. And for chemists, the complex organic molecules refer to larger molecules, the polymer-like ones. So, for example, proteins. And where can we find such interesting molecules in space? So mainly in the cold interstellar environments, like, for example, gas clouds, other globes' atmospheres, or comets. And take a look at those pictures. So here we have the Taurus molecular cloud 1 and the Saturn's moon Titan. And here the scientists found complex organic molecules. Those photos are provided by the European Space Agency. So when we are talking about what kind of molecules were found in the interstellar medium, we have hundreds of possibilities, but I would like to highlight the three examples here. So we have the acetonitrile, benzene, and benzonitrile. And why do I mention this? Because these were found in the Taurus molecular cloud 1. And this is quite an interesting thing. I will get to that soon. But when we talk about such molecules, we have even more complicated in structure and more complicated ones, like, for example, naphthalene. But why benzonitrile? Why is it so interesting? So I mentioned a little bit more complicated structure like the naphthalene, but benzonitrile is also among the most complicated organic molecules found in the interstellar medium. And another interesting thing is when you look at how it's built, you can see the nitrile group. And this is something not peculiar, of course, but this is important because such molecules can be mentioned in context of the precursors to some biogenic molecules, like, for example, nucleobases and their alternatives. So how do we research such organic molecules? We start from the detection techniques because we need to detect them. And one of particularly important tools in astrochemistry is the spectroscopy. So through the use of telescopes, we measure the absorption and emission of light from molecules and atoms in environment. And among most powerful techniques for detection of individual chemical species is radioastronomy. And this has resulted in the detection of over 100 of interstellar species. And they include ions, radicals, and the organic compounds, such as alcohols, acids, aldehydes, and ketones. And another tool worth of mentioning when we are talking about the detecting organic molecules in the interstellar medium is the infrared spectroscopy. And this kind of tool revealed that the interstellar medium contains a suite of complex gas phase carbon compounds that we call the polyaromatic hydrocarbons. So when we detect our molecules, we gain knowledge, and we can also conduct some laboratory experiments. And in the context of astrochemistry, we need to apply conditions which are present in the interstellar medium. So such experiments involve high or ultra-high vacuum. Cryogenic temperatures is similar to those found in the, for example, molecular clouds, and the UV source that will simulate the UV exposure in interstellar medium. Also, spectroscopic methods and mass spectrometric analysis are among the most popular ones when it comes to laboratory experiments. And for computational chemistry, we can use this tool to model, for example, reaction paths in the interstellar medium, or we can make our research easier because it's easier to replicate such harsh conditions of space via simulations, for example, molecular dynamics or quantum chemistry, then it's made in the laboratory. So now let's get to a short introduction about what is AI. And this is a wide-ranging branch of computer science concerned with building smart machines capable of performing tasks which typically require human intelligence. And most AI examples known nowadays rely heavily on deep learning and natural language processing. So by utilizing these technologies, the computers can be trained to do specific tasks. So they process large amounts of data and recognize patterns in such data. And AI works by combining large amounts of data with intelligent algorithms and fast iterative processing. And this allows the software to learn automatically from the patterns or features in data. And we have three major subfields of AI: machine learning, neural networks, and deep learning. So starting from machine learning, this one automates the analytical model building, and it uses methods from neural networks, statistics, operations, research, and physics. So with this, we can find hidden insights in data without explicitly being programmed for where to look or what to conclude. Now we proceed to neural networks. And the neural network is a type of machine learning that is made up of interconnected units. So we can compare them to neurons in humans' brain. And such neurons process information by responding to external inputs. And these rely and the information are relied between each such neuron. And this process requires multiple passes at the data to find connections and derive meaning from undefined data. And we have the deep learning. So the deep learning uses the huge neural networks with a lot of layers of processing units. And it takes advantage of advances in computing power and improved training techniques. So it can learn more complex patterns in large amounts of data. So, for example, if you have some speech recognition and image recognition, this is thanks to the deep learning. Okay, but what is this that chemistry between space and AI. So we can apply some AI concepts in astrochemistry. And what are prospects? Because for many years we used more, let's just say, traditional methods, like, for example, Fourier transfer infrared spectroscopy for detection of molecules in the interstellar medium, laboratory experiments for further investigation, or even molecular dynamics for modeling. And they come with their limitations. We can use AI to overcome such limitations. Let's take a look at those limitations. So, for example, for the detection techniques, they may be not sensitive enough to detect some molecules present in the space environment. And for example, this is the case for the radio spectroscopy that I mentioned before. Because in order to use such a method, we have to have the dipole moment in our molecule. And as we know, not every single molecule has this dipole moment, so they can be, for example, omitted by this method. For laboratory experiments, I mentioned it briefly before, those harsh conditions are extremely hard to reproduce in the laboratory environment. So we can use computational chemistry or molecular dynamics to aid ourselves with such tasks. But we have another problem. So we handpick features of molecules, and it may be simple to implement, that's true. But certain features may only occur in certain groups of molecules. And if we handpick features, this will be neither scalable nor balanced in their approach to representations. But we can use all the data gathered from such experiments, so from spectral analysis, from laboratory, molecular dynamics, or quantum chemistry, combine them with each other, and create AI models, or just create AI models only on the basis from, for example, spectral data. And an interesting thing, and a good starting point, because this is quite a novel thing, is using the data gathered from the Taurus molecular cloud 1 to create a model which will help with identifying the new molecules that can be subjects of the astrochemical research. So there are many possibilities, and this will conclude what I mentioned on previous slides, because we have tons of organic molecules in space, and some of them we are aware of, we found them, we research them, but some of them are not known for us. And we can apply AI for this purpose. So we can find new candidates for astrochemical research, just like the research involving the data from Taurus molecular cloud 1, or we can use the already known reaction paths to discover new possible reaction mechanisms and reaction paths from the substrate 8 to product B, because we don't know if the one that we recently discovered is the only one. There may be more of them. So why not build the AI model for this? Or we can research various effects of conditions in the interstellar medium. So for example, various abundance of the UV radiation, how it affects the reaction paths. So as you can see, the chemistry between the space and AI is quite real. So thank you very much for your attention. And if you have any questions, feel free to ask. And also the slide with the literature if anyone is interested. So once again, thank you very much.
Thank you very much for this presentation. So I'm not sure whether there are any questions, but we can wait like for 1 or 2 minutes. But that was very interesting and in our subject. So thank you. We do have another session straightly after this, which is also about artificial intelligence, search for life, and astrochemistry. Well, let's maybe wait for 1 or 2 minutes. Yeah, but you were very straightforward and direct about what you were saying, so I guess everyone really understood you well. So that's probably there are no questions. Yeah, I agree with the comment. Very nice talk.
Thank you very much. So I guess there really aren't any questions.
Yeah, I guess so. All right, so I guess we can cut it here. Again, thank you very much for the presentation.